In this section, we'll be defining linear combinations and looking at some examples. Let's start with the definition of linear combination. We're going to assume we're given a set of vectors, v1, v2 through vp, and these vectors are in Rn. What that means is simply that each vector has n entries. We're also going to be given a set of scalars, c1, c2 through cp. These scalars are just real numbers. Then we're going to say the vector x, which is defined by c1 times v1 plus c2 times v2, etc. through cp plus vp, is going to be called a linear combination of the vectors v1 through vp using the weights c1 through cp. Let's look at an example of a linear combination. Suppose I want to look at 2 times the vector 1, 0 plus 3 times the vector 4, 2. This combination, if I compute it, I would get 2 plus 12, or 14, and 0 plus 6, or 6. In this case, I'd say that the vector 14, 6 is a linear combination of the vectors 1, 0 and 4, 2, and in this case, I used weights 2 and 3. Let's now look at an example working backwards. Suppose I've given you the vector 4, negative 13, and I'd like to know, is that vector a combination of v1 and v2? Well, let's look at what that would mean given our definition. In order for this to be a linear combination, the vector 4, negative 13 would have to be writable with constants c1 times the first vector plus c2 times my second vector. In other words, 4 would have to be equal to 2 times c1 plus 3 times c2, and my negative 13 would have to be equal to 5 times c1 minus 4 times c2. Notice here I have a set of two equations and two unknowns, c1 and c2. So figuring out whether the vector x is a linear combination of v1 and v2 is equivalent to solving the set of two equations and two unknowns. There's a variety of methods to solve that based on high school algebra methods such as elimination or reduction, or we could solve it using the techniques we've learned in our linear algebra course. In this case, I'm going to turn this into an augmented matrix and solve by row reduction. This is the augmented matrix 2, 3, 5, negative 4, augmented with 4, negative 13. I can now perform a series of row operations to put this in reduced row echelon form to help me quickly determine the values of C1 and C2 for which this holds. In this case, if I fast forward, my matrix reduces to 1, 0, negative 1, 0, 1, 2. This tells me that my constant C1 is equal to minus 1 and C2 is equal to 2. If I look back to my original equation over here, you can verify that if you plug in C1 equal to negative 1 and C2 equal to 2, this equation does indeed hold. So therefore my conclusion is that 4, negative 13 is a linear combination of v1 and 2. Let's now look at a theorem. The theorem says the vector equation x1 a1 plus x2 a2 on up to xn an equals b has the same solution set as the linear system given the augmented matrix shown here. In other words, this says b can be generated by a linear combination of a1 through an if and only if there is a solution to the corresponding linear system. This theorem is actually really useful. It tells us the system ax equals b has a solution if b is a linear combination of the columns of A. So in other words, if we could somehow figure out all possible things that are a linear combination of the columns of A, we would then be able to see if b was amongst that set, we would then know that the system had a solution. We'll look at this further in the future. That concludes the lecture on linear combinations.